Hello, everyone. Good morning. I hope all of you are doing fine. I'm okay. I'm doing mathematics. Okay, so today we do section 4.4. Section 4.4. Instantly independent. Stochastic processes. In the previous lecture, I mentioned about stochastic processes which have very special property for our new integral. And that special property is what I call instantly independent stochastic processes. So suppose Bt is a given Brownian motion, and we have the filtration given by the Brownian motion. This is the observation. You see, for the integrand B1 that we discussed before, it is decomposed into two pieces, Bt plus B1 minus Bt. And this part here is adapted so that we can apply the Ito theory. And this part is the spatial property. The spatial property, what is this spatial property? Is this stochastic process B1 minus Bt. For each t, it is independent of Ft for each t. And so I'm going to make the abstract concept of this spatial property, and that is given in this definition. So this definition comes from this observation. A stochastic process xt for t between A and B is called instantly independent of the filtration F sub t if for each t the random variable xt and ft are independent. That is, the sigma field generated by xt and the sigma field ft are independent. And therefore, you see, this is the first example of instantly independent stochastic process. The concept comes from this example, and then we make an abstract concept of this observation, and that's what we call instantly independent. And of course, you see, there are many, many more instantly independent stochastic processes. For example, B1 minus Bt. If we take square, this is instantly independent. Or any Fourier function, theta, and then B1 minus Bt. This is also instantly independent, and so forth. Okay, we turn to next page. This is page 16. Okay, so now we have one adapted stochastic processes. Okay. And this is the Ito part. And in addition, we have instantly independent stochastic processes. And this is what I would refer to as the counterpart of the Ito theory. And now we have this theorem. Suppose a stochastic process xt is both adapted and instantly independent. Suppose that. Then, what is the conclusion? Then, this stochastic process, xt, is a deterministic function. So only the class of deterministic functions the function there can be both adapted and instantly independent. This is almost obvious, but let me give you a proof. Since xt is adapted, this implies the conditional expectation of xt given ft is xt, almost surely, for each t. And on the other hand, the assumption that xt is instantly independent imply the conditional expectation of xt given ft is the same as expectation of xt is a constant, is a constant depending on t, so it is a function, or it is a deterministic function of t. And now, since x is both adapted and instantly independent, therefore xt equals to expectation of xt for ht, and so xt is a deterministic function. Deterministic function. So this property is pretty obvious. Okay, we turn to the next page. Now we make a, by the way, this is page 17. By the way, now we make a, a critical observation. You see, we have used this as a motivation for the new stochastic integral. And it is given by the limit f evaluation at the left endpoint, and this evaluation at the right endpoint, and Brownian motion increment Ti. Suppose we have two representations of the integrand. Ft and phi t and gt times ct. Does this imply the limit equal to the limit well, it is not so obvious the limits are the same, because ft phi t equal to gt psi t does not imply f t sub I minus 1 phi ti equals to g ti minus 1 psi ti. So see, this does not this in general, this is of course not true in general. And so whether these two limits are the same or not, it is not so obvious. We will address this question in the next video.